Okay, hello, I'm Sajjad. Today I want to present my work Sphinx, a succinct perfect hash index for x86. This is a joint work with my supervisor named Diane at the University of Toronto. So let's first refresh our memory. We know hash tables, right? Hash table, they have a table, and each key would be directed to a specific slot in the hash table based on the hash value of that key. So obviously we could have a situation that two keys are directed to the same slot, but it's not a very big deal because we have the actual keys stored in the slots, and we can use some techniques like chaining or linear probing to resolve the collision. So we call a hash table perfect whenever it's collision free, but at the same time we are not storing full keys. So that's the tricky part. And obviously, if we are also able to support writes, like update, insert, and deletes, we call it a dynamic perfect hash table. And there are many applications for something like that in file system, flash translation layer, and key value stores. So there are many existing dynamic perfect hash tables. I will just talk about two of them today because I just want to sketch the design space for us to understand the disadvantages each one has. The first one is FKS, introduced at JACM 1984. So the intuition at FKS is assume you have n keys and n slots. You distribute the keys based on the hash value of each one of the keys, and obviously some keys can collide. And then you allocate a secondary hash table with a size proportional to the power of 2 of the number of collisions in each occupied slot. And then you brute force another hash function until there is no collision in the secondary table. So for each table, we have another hash function we need to brute force. So this is nice, but many slots would be wasted in this design. The second dynamic perfect hash table is DHT, introduced and presented at VLDB 2021. It is actually used in the industry in a company named PlayUps. So the idea is the same. At first, we just have n keys and slots. We distribute the keys, and some keys collide, but then we build a trie over the first differentiating bit of the hashes of the keys. And with that, we can resolve the collision. So without storing full keys or very long hash digest of the key, we just store the bits that matter during differentiating of the keys to resolve the collision. And then we store succinct encoding of each one of these tries, but because tries are of different sizes, we end up with variable size encodings, but on average it's 4 bits per key. But again, because it's variable length, it's going to be slow on CPU. So you can imagine you're querying for the, let's say, 33rd slot. Because you don't know the location of the 33rd slot, you need to go and decode all of the first 32 slots up until the 33rd to reach to the location that you are actually interested in. So we saw that FKS is space inefficient, DHT is CPU inefficient. The question is, can we do better or not? Or more concretely, can we build a compact perfect hash table that allows very fast CPU operations? And thanks to x86 optimize rank and select commands, the answer is yes. So let me talk about rank and select a little bit. Assume you have a bitmap B, shown in this example, and you want to calculate the number of set bits up until an index, let's say index I. So this is exactly what rank does. So rank BI counts the number of set bits in B up until index I. So for example, rank B3 is going to be 2. We can pop popcount, which is a specific instruction on x86 to speed up calculating rank on x86 CPUs. On the other hand, select BI finds the offset of the ith set bit in B. So for example, select B3 finds the third set bit's offset, which is in this case is 4. And we can use tz count and pdep to speed up calculating that on x86. TZ count stands for trailing zero count, and PDEP stands for parallel bit deposit. So with that in mind, we introduce Sphinx. Sphinx, first of all, is a perfect hash table. It's actually a dynamic perfect hash table, which means it doesn't have any collisions without storing full keys. It's very succinct, meaning we are only storing 4 bits per key on average, and it's going to be blazing fast on x86 CPU. So the challenge in the Sphinx is actually to store as few bits as possible, but at the same time be able to use rank and select in favor of CPU operations to speed up CPU tasks. So to give you the high-level structure of Sphinx, Sphinx consists of fixed size blocks, each one of them consisting of variable length slots. And the reason for these hierarchical structure is that these slots are very small but variable in length. So we pack them together and put them in a block for the block to absorb this variation and end up being very memory efficient. So suppose you have a key with the hash shown here. The first 2 bits of the hash in this example is going to be corresponding to the block index, next to corresponds to the slot index, and the rest is a fingerprint. And then with that, we can allocate the location of the succinct encoding of that specific fingerprint. And if you look at it, this design is going to sort all the keys based on their hash values. So if you have 2 keys with the same block index and slot index, this structure is going to sort it based on the fingerprint. And obviously, if the block index or slot index is lower than another one, it's going to be reside in a smaller slot index or block index. So implicitly, this structure sorts the keys. So I will talk about 3 parts of our design. The first part is the slot encoding. And first of all, let me say that our approach draws much inspiration from DHT. And now let's assume you have 3 keys being mapped to the same slot. So it's just an example with the hashes shown here. We want to distinguish between these hashes, and we see that the first differentiating bit is actually at offset 0, meaning offset 0 differentiates or separates hash 2 from hash 1 and hash 3. Also, between hash 1 and hash 3, the first differentiating bit is at offset 2. So now we have a data structure shown on the left side of the slide that can resolve the collision without actually storing full hashes or full keys. We just need to store this differentiating bits at each stage of this trie. So now the question is, how can we encode this succinctly as possible? So each node has 2 pieces of information. The first piece is the child type of each node, and we denote leaves with zeros and internal nodes with 1. So for example, for the root node on the left side, we say it's an internal node. On the right side, it's a leaf node. We denote it with 1, 0. The second piece of information is the distance from the parent, which we denote in with one terminated unary. And here we assume the root's parent is at index -1. It's just a small assumption to make sure that all distances are going to be positive numbers. And also by one terminated unary, I mean, we're going to map 1 to a single set bit, 2 to 0 and a set bit, and etc. So again, back to our root node, the distance from its parent is going to be 0 minus -1, which is 1, and we denote it with a single set bit. Then we continue with the first left internal node and just do the same thing again. So in this case, both of its children are going to be leaves, so we denote them with 0 and 0. And the distance from the parent, which in this case is the root, is 2, so we denote it and represent it with 0, 1. Also, if you look at this structure very closely, you see that the last 2 bits of the first field represent the last internal node's children, meaning that always the children are going to be leaves because there is no other internal node. So we can just remove that part. And then by concatenating the first and the second field, we end up with the slot encoding. Also, we add a single set bit at the end of the slot encoding. This later helps us delimit the slots, and I will show you how next. So now let me talk about the block structure. And remember, a block consists of contiguous slots packed together, and the block implicitly sorts the keys based on the hash value of the keys. So let's get into that. And now, again, with another running example, assume we have 6 keys that are being mapped to this block. In this example, the first 2 bits correspond to the slot index, meaning that in total we have 4 slots, and the rest corresponds to the fingerprint. Our block starts with a segment that is responsible to answer this question: is the slot occupied or not? So the first 4 bits is enough for answering something like that. In this case, slot 0 is occupied, slot 1 is occupied, slot 2 is not occupied, and slot 3 is occupied. The second segment of the block stores the number of entries in each occupied slot, and we use one-terminated unary for that. Again, we use unary encoding here because most of these slots only have 1 entry, and we only need to store a single bit for each one of them. So in this case, slot 0 consists of 1 entry, so we store a single set bit for that. Slot 1 has 2 entries, we store 0 and 1 to represent that. And slot 3 has 3 entries, and we store 0, 0, 1 to represent that. At last, we store the encoding of the tries. And remember, we only need to build a try to resolve the collisions, and that only happens whenever we have 2 or more than 2 entries in a slot. So in this case, slot 1 has 2 entries, which we know how to build a try and how to encode it. We store the encoding at the beginning of this structure. Also, slot 3 has 3 entries. We build a try for that and store the encoding at the end of the block. So this is going to be our block structure at the end. And I just want you to note that we tried so hard to build a linear pattern between the number of entries and the number of set bits. So as you can see, the formula is suppose you have n entries in the slot, the number of set bits or the number of ones in that specific slot is going to be 2 times n minus 1. So now that the number of ones is predictable, we can use select operation to pass over those useless number of ones to reach the slot that actually we care about and want to decode. To make it more concrete, let's say we query for hash 5. And we know hash 5 resides at slot 3, the target slot. So we just need to count the number of set bits before the target slot. In the first 4-bit, the first segment, we know by definition, each set bit corresponds to exactly 1 occupied slot. So we just use rank over the first 4 bits of the block to calculate the number of set bits here. In this case, that number is 3. In the second segment, again, each occupied slot corresponds to exactly 1 set bit. So we just double the number that we calculated before. So that's going to be 6 up until now. And at last, if you sum over the 2 times n minus 1 formula that I showed you, you end up with the formula shown here. It's not super important. The punchline here is that now we are able to use this predictable pattern to exactly know how many set bits reside at the last segment. In this case, that number is 2. So we just need to pass over 8 set bits to reach the start of the target slot. And then we can proceed decoding the target slot. So now let me talk about decoding tries. So the thing with these try encodings is that there are complicated kind of encodings to decode, and we need to resort to bit-by-bit traversal that causes a bunch of branch mispredictions. So it's not great in terms of CPU. But at the same time, we know that most tries only have 2 to 4 entries. So we can exploit this skew in our favor. Our idea, our intuition here is to make a decoder, a pre-computed decoder that decodes the common slots very fast. Actually, in our case, we use this decoder for 98% of the situations. So that's going to help us a lot. So let me give you a deeper intuition. We build a decoder which consists of an offset for each possible permutation of the differentiating bits. So again, another running example. On the right side, you see a try, and we see that offset 0 and offset 2 are the differentiating bits. So we build a table for that. What if bit 0 and bit 2, both of them in a fingerprint, are zeros? Then we know we are going to be directed to hash 0 at offset 0, right? And also, if bit 0 is 0, bit 2 is 1, again, we're going to be directed to offset 0. But now, if bit 0 is 1, bit 2 is 0, then we first go to the right and then go to the left, which directs us to offset 1. And if both bit 0 and bit 2 are 1s, we're going to be directed to hash 2. So we pack these offsets together and create a table for that, and we store it someplace in a pre-computed location before running our system. And now let me show you how query works and how query can use that table. So let's say we are querying for a key that is being mapped to this specific slot. So we know that the try corresponds to this fingerprint. And because we know in this try only bit 0 and bit 2 matter, we just need to extract those. So we use pextract, which is a x86 instruction, to extract those 2 bits. And then we read the decoder at that specific offset. And the value of that directs us to the offset that the hash resides, which is offset 1. And that was almost it. We saw how Sphinx is a perfect hash table. It is succinct and it's blazing fast, but Sphinx is a full and complete system. It supports fine-grained expansion. It supports overflow management. It is a highly concurrent and scalable system. So please, if you're interested, check out the paper. And to just show you some results, we benchmark Sphinx against many baselines and in many benchmarks, but in a specific case of query and update latency, we can see that Sphinx dominates DHT. And thank you for listening. Here's a link to the paper. And if you're interested, please contact me with my email. Thank you.